So this simulation helps us to look at the relationship between the distribution of positive charges within an atom and the strength of the electric field, which ultimately is going to determine the path that the alpha particles can take. So look at the things that we can manipulate here. We can either have the positive charges evenly spread throughout the atom, and this is representative in the plum pudding model, aka the blueberry muffin model or the watermelon model. Then we can also change them so that they're a little bit more closer together, and also highly concentrated means like right on top of each other. All right. So let's go back to what we currently know about the model of the atom, where the positive charges are spread evenly throughout the model. And let's go ahead and look at the electric field. So notice the green arrows surrounding it. Would you say that those are strong or are they weak? Now let's go ahead and shoot an alpha particle at this, and let's observe the path that that alpha particle takes. We're going to let this run for a few moments just to make sure that we get a really solid observation of what's happening. But it looks as if the alpha particles are just passing straight through the atom. There's no deflection, aka there's no like bouncing off of the atom. So does this match our observations with Rutherford's gold foil experiment? Let's hit stop. I'm going to click reset. And now let's bring some of those positive charges a little bit closer together. Not highly concentrated, but just like a little bit closer. What do you notice now about the electric field compared to when they were more spread out? What you should be noticing is a change in the intensity of the green color, and that should relate to the strength of the electric field. Now let's go ahead and shoot some more alpha particles at it, and let's see what happens. What you should be noticing is that we are starting to see some deflection. Those alpha particles, remember, are positively charged, and they're coming near this a little bit concentrated positive clump of charge here in the atom. And some of those alpha particles are bending away, right? We know that that should happen because positives and positives, they don't want to be next to each other. They're going to repel. However, we are still seeing some alpha particles completely pass through the atom, which we did observe a little bit, but we're not seeing like the real strong bounce back, that 1 in 10,000 that were just like shocking to us, because that just doesn't, that's new and different. So let's hit stop, reset, and let's make a highly concentrated clump of positive charges. Notice the size of it is much smaller, but then also notice the strength of the electric field surrounding it. Let's go ahead and shoot some alpha particles at that and make some observations of their pathway. We're going to let this run for a few moments. What you should start noticing is that the alpha particles are deflected even more than when we had kind of a medium concentrated clump of positive charge in our atom. I'm hoping that at some point along here, we will see one of these alpha particles run directly into this positive clump here, because if that does happen, I've seen it before, I promise. If that does happen, it does bounce immediately right back towards where the alpha particle came from. Now, this matches our observations the best. So things to remember: how are the positive charges distributed? What is the strength of that electric field coming from the atom, not the alpha particles, but coming from the atom? And does that match our observations of the pathway the alpha particles took? Did you see that? It happened! Huzzah! Perfect. So take this knowledge with you as you answer the next few questions.